Hello everyone, my name is Ferhat Özgür Çatak from the University of Stavanger, Norway. In this talk, I will present our work titled Comparative Analysis of Attention Mechanisms for Automatic Modulation Classification in RF Signals. The focus of this work is understanding how different authentication attention mechanisms affects both accuracy and computational efficiency in modern modulation classification systems. This is talk outline. I will start with a short motivation and problem definition. Then I will introduce our CNN transformer, hybrid architecture and attention mechanisms we study. After that, I will describe the experimental setup and the dataset. Finally, I will present our key results, practical insights, and featured directions. So why AMC and why attention? Modulation Classification, or AMC, is a core component in modern wireless systems, especially for cognitive radio, spectrum monitoring, and interference-aware communications. Traditional feature-based approaches struggle to generalize under changing channel conditions. Deep learning, or particularly CNNs, has improved performance significantly. However, CNNs mainly capture local spatial patterns, while radio signals also exhibit strong temporal dependencies. This motivates the use of attention mechanisms, which are very effective at modeling long-range dependencies. The key question we ask is, how does the choice of attention mechanisms affect performance and efficiency in AMC? This is our contributions. Our main contributions are fourfold. First, we propose CNN transformer hybrid architecture, especially designed for IQ signals. The second, we perform a systematic comparison of three attention mechanisms: baseline multi-head attention, casual attention, and sparse attention. Third, we analyze both accuracy and inference time, which is critical for real-time systems. Finally, we provide a per modulation analysis, showing which modulation types benefit from local or global attention. This is our system overview. This slide shows the overall system architecture. The input consists of complex valued IQ samples, which are reformulated as two-channel real-valued tensor. A CNN extracts local spatial features from these samples. The extracted features are then passed to transformer blocks with the different attention mechanisms, followed by a global pooling layer and classifier. The design allows us to separate local feature extraction and temporal dependency modeling. CNN transformer hybrid architecture. The CNN consists of two one-dimensional convolutional layers which batch normalization and relay activations. The transformer part contains two layers with four attention heads and feed-forward network. Residual connections and layer normalization are used for stable training. Finally, a lightweight MLP produces the modulation classification output. This hybrid design combines the strength of CNNs and attention-based models. Attention variants. We examine three different attention mechanisms. The first one is baseline. Baseline attention allows full bidirectional interaction between all time steps. It provides maximum modeling capacity but has quadratic complexity. Casual attention restricts attention to past and the current samples only. This is well suited for real-time and streaming applications. Sparse attention limits attention to a local temporal window, significantly reducing the computational cost while preserving local temperature structure. These mechanisms represent different trade-offs between expressivity and the efficiency. Dataset. We evaluated our approach on a publicly available datasets. It is widely used benchmark of AMC. It contains 2020 220,000 IQ samples across 11 modulation, including both digital and analog modulations. Each sample has 128 complex points generated over SNR values from -20 to 18 decibel. In our experiment, we focus on the practical SNR range from -6 to 18 decibel and split the data into training, validation, and uh, test sets. This is our implementation details. All modules are implemented in PyTorch. We use the AdamW optimizer with cosine learning rate scheduling and early stopping. Gaussian noise injection is applied as a data augmentation to improve the robustness. We evaluate models using accuracy, macro F1 score, inference time, and parameter count. This is our overall performance. This table summarizes the overall performance. The baseline attention model achieves the highest accuracy at 85%. Casual and sparse attention models achieve slightly lower accuracy, but still remain above 83%. Importantly, all models have the same number of parameters, allowing for a fair comparison focused on the attention behavior. This is this figure shows highlights inference time differences. Casual attention achieves the 83% reduction in the inference time, while sparse attention achieves a 75% reduction compared to baseline attention. These results shows that attention design has a major impact on real-time feasibility, even when accuracy differences are relatively small. Per modulation analysis. This slide shows the F1 scores for each modulation style. We observed that simpler modulations such as CPFS key, GFS key, and PAM4 often benefit from sparse attention, indicating that local temperature context is sufficient. In contrast, complex modulations like QAM16 or 64 require global context and therefore perform best with full attention. Analog modulation, especially WBFM, remain challenging for all the models. F1 distribution. The F1 score distribution shows that baseline attention has a slightly higher median performance. However, the overlap between distribution indicates that casual and sparse attention provides competitive performance at much lower computational cost. Confusion matrices. The confusion matrices reveal consistent error patterns. QAM 16 and 64 are frequently confused due to similar constellation structures. AMDSP and WBFM also has cross-confusion, reflecting sharing spectral characteristics. Digital modulations such as BPSK or QPSK are classified robustly across all models. Deployment guidance. These results suggest clear deployment guidelines. If maximum accuracy is required and resources low, baseline attention is preferred. For real-time, low-latency systems, casual prevention attention provides an excellent balance. For the edge or embedded deployments, sparse attention offers strong efficiency with minimal accuracy loss. There are several directions for the future work. First, a more detailed analysis across SNR ranges could provide deeper robustness insights. Second, evaluating under realistic channels effects such as fading and multipath is important. Finally, adaptive attention mechanisms that change dynamically based on signal characteristics could further optimize performance efficiency and trade-off. In conclusion, We present a comparative analysis of attention mechanisms for automatic modulation classification. Our, our CNN transformer hybrid achieves stroke performance on the publicly available datasets. While baseline attention yields a highest accuracy, casual and sparse attention dramatically reduce inference time with only minor performance loss. These findings provide a practical guidance on designing efficient AMC systems in next-generation wireless communication systems or networks. Thank you for attention.